We now start module 4 of chapter 4, where we will be talking about minimal polynomials and a criteria for diagonalizability in terms of minimal polynomial. We first introduce the concept of invariant subspaces and use that to prove a very important theorem called the Cayley-Hamilton theorem. And then this Cayley-Hamilton theorem will be used when we define the minimal polynomial for a linear operator, and finally when we prove criteria for diagonalizability. Let V be a vector space over a field F and T a linear operator on V. A subspace W of V is called a T invariant subspace of V if T of W is contained in W. Another definition: suppose that V is a non-zero vector in the vector space V, then the subspace which we denote by T suffix V, which is the span of the set of vectors V, TV, T square V and so on, is called the T cyclic subspace generated by the vector V. Examples: the trivial subspace, that is singleton zero vector, the whole space V, the subspace range of T, kernel of T, the eigenspace is n lambda for eigenvalues lambda, and the T cyclic subspaces TV are examples of T invariant subspaces of a vector space V. And another example, if we consider the rotation operator T pi by 2, which is rotation by an angle pi by 2 in the real plane R2, and if we choose a non-zero vector V in R2, then it is easy to see that the T cyclic subspace T pi by 2 V is nothing but the whole of R2. Theorem: let V be a vector space of dimension n over the field F and T a linear operator on V. Let W be a T invariant subspace of V. Then if we look at the operator T restricted to W, the characteristic polynomial chi T restricted to W divides the characteristic polynomial chi T over the field F. W is a T invariant subspace, therefore by definition T of W is contained in W, and that is why T restricted to W is indeed a linear operator on W. So this characteristic polynomial of T restricted to W makes sense. To prove, start with an ordered basis for W given by the set containing the vectors V1, V2, Vk. Let us call this set B dash. Extend B dash to an ordered basis B for V, which is given by this set V1 etc. up to Vk, and then Vk plus 1 etc. up to Vn. Let A denote the matrix representation of T with respect to the basis B, and A dash denote the matrix representation of T with respect to the basis B dash. Then the matrix A is of this form written in blocks. So, the top left corner is A dash and then B, and in the second row you see 0 and C, where B and C are matrices of suitable size and 0 is of course the 0 matrix. Therefore, the characteristic polynomial of A, which is chi A t, is determinant of A minus t I n, and that is determinant of A dash minus t I k, B 0, C minus t I n minus k. You can see that A dash is a k cross k matrix, because it is the matrix representation of that operator T restricted to W with respect to the basis B dash, and this size of the matrix A has to be n cross n. Therefore, in the bottom right corner the matrix C has to be of size n minus k. And now if we compute the determinant, then it is the characteristic polynomial of T restricted to W multiplied by determinant of C minus T I n minus k. Therefore, we have proved that the characteristic polynomial of the restricted operator, that is T restricted to W, divides the characteristic polynomial of T. Let us now state a lemma which is somewhat technical in nature, but it will be used to prove the Cayley-Hamilton theorem. It says the following: let T be a linear operator on a finite dimensional vector space V over F. Let small v be a non-zero vector in V such that the dimension of the T cyclic subspace T V is k. Then the first part says that the set of vectors V, T V, T square V and so on, T to the power k minus 1 V is a basis for the subspace T V, and if we take this non-trivial linear combination of the vectors V, T V, T square V and so on up to T k V, such that A0 V plus A1 T V plus A2 T square V and so on A k minus 1 T k minus 1 V plus T k V is the 0 vector, then it can be proved that the characteristic polynomial of the restricted operator, that is chi T restricted to W, is nothing but minus 1 raised to k multiplied by A0 plus A1 T plus A2 T square and so on A k minus 1 T to the power k minus 1 plus T to the power k. So, what is interesting here is that a cyclic subspace can be seen very explicitly, and in fact this is a basis, and that can be used to prove that the characteristic polynomial of the restricted operator is of this form. A quick definition: let f t denote this polynomial A0 plus A1 t and so on up to A k t to the power k. In f t, that means the coefficients of the polynomial are in the field f. Let t be a linear operator on V. Then f of t is defined as A0 I plus A1 t plus A2 t square and so on A k t to the power k. I denotes the identity operator and t to the power I denotes composition of t I times, and it is very easy to verify that f of t is also a linear operator on the vector space V. Now, the Cayley-Hamilton theorem. Let T be a linear operator on a finite dimensional vector space V over the field F, then chi T of T is the 0 operator on V. And chi T of T is the polynomial chi T evaluated at T by the previous definition. Let us prove this theorem now. Let small v be a vector in the vector space V. If small v is the 0 vector, then chi T of T on V produces the 0 vector, because chi T of T is also a linear operator on V. Suppose that V is a non-zero vector. We now show that chi T of T of V is the 0 vector, and that would prove that chi T of T is the 0 operator on V. Consider the T cyclic subspace T V. If dimension of T V is k, then there exist scalars A0, A1 and so on up to ak minus 1 in F, such that A0 V plus A1 T V plus A2 T square V and so on ak minus 1 T to the power k minus 1 V plus Tk V is equal to 0. Recall that V, T V, T square V and so on up to Tk minus 1 V, they form a basis for the T cyclic subspace T V, and dimension of T V is k. So, any k plus 1 vectors would be linearly dependent, and that is why we get such a non-trivial linear combination. And by that lemma which we stated, characteristic polynomial of T restricted to T V is given by that polynomial minus 1 raised to k multiplied by A0 plus A1 T and so on ak minus 1 T to the power k minus 1 plus T to the power k. Therefore, chi T restricted to T V of V is minus 1 to the power k multiplied by A0 V plus A1 T V and so on ak minus 1 T to the power k minus 1 V plus Tk V, and that is equal to the 0 vector. We know that chi T restricted to T V of T, that is the characteristic polynomial, divides the characteristic polynomial of T over the field F. So, we can write chi T of T is G T multiplied by chi T restricted to T V of T for some polynomial G T in F T, and therefore, chi T of V is G T of chi T restricted to T V of V, but chi T restricted to T V of V is 0, therefore, G T of 0, and that is 0. The analogous version of Cayley-Hamilton theorem for matrices follows from the previous theorem. So, suppose that A is an n cross n matrix over the field F. Let chi A T denote the characteristic polynomial of the matrix A, then chi A is the 0 matrix over F. Well, we just apply the Cayley-Hamilton theorem for linear operators on the linear operator L A, and that gives us this result. We have proved that T satisfies the characteristic polynomial. That means, if chi T denotes the characteristic polynomial of the operator T, then chi T evaluated at T is the 0 operator. Now, we are ready to define what is called a minimal polynomial for a linear operator T. As the name suggests, the minimal polynomial would be a polynomial which is satisfied by the operator T and minimal in the sense that it has the least degree. Let us start with minimal polynomial and then see another criteria for diagonalizability of the operator. Let V be a finite dimensional vector space of dimension n over the field F, T a linear operator on V. We know by the Cayley-Hamilton theorem that chi T of T is the 0 operator on V. In other words, T satisfies the polynomial chi T of T over F. There is at least one polynomial in the polynomial ring Ft which is satisfied by the operator T. Let us now choose a monic polynomial of the least positive degree satisfied by T and call it Mt. We know by the well ordering property of the set of natural numbers that we can indeed get one such polynomial which is of the least positive degree, which is monic and which is satisfied by the operator T. We know that the division algorithm is true in the polynomial ring Ft. And we can apply division algorithm to show that if Ft is a polynomial over F satisfied by T, then Mt must divide Ft over F. Well, how to see that? First of all, we can use division algorithm on Ft and Mt to write Ft is equal to Qt into Mt plus Rt, where Qt and Rt are unique polynomials, and we also know that the polynomial Rt, which is called the remainder, is either the 0 polynomial or degree of Rt is strictly less than degree of Mt. That is by the division algorithm. But then if we evaluate this expression for the operator T, then we will see that R evaluated at the operator T becomes the 0 operator, but then the polynomial Rt has to be the 0 polynomial, otherwise we will get a polynomial whose degree is smaller than the degree of Mt, which is of course not possible because Mt is a monic polynomial of the least positive degree satisfied by T. Moreover, by the monic condition on Mt, it follows that Mt is the unique monic polynomial over F of the least positive degree such that M of the operator T is the 0 operator. This polynomial is usually denoted by M suffix the operator T of little t, and this is called the minimal polynomial of the operator T over the field F. The analogous version for the minimal polynomial of the matrix A would be, if A is an n cross n matrix over the field F, then the minimal polynomial of A is the unique monic polynomial MAT over the field F of the least positive degree, such that MA of A is the 0 matrix. Theorem: let lambda be a scalar in the field F, then chi t of lambda is 0 if and only if mt of lambda is 0. In other words, the characteristic polynomial and the minimal polynomial have the same zeros. We know that the minimal polynomial of t divides the characteristic polynomial of t, and that is by the division algorithm for polynomials. Therefore, we can write chi t of t is mt of t multiplied by qt for some polynomial qt over f. Therefore, if mt of lambda is 0, then chi t of lambda is 0. Now, we prove that if chi t of lambda is 0, that is, if lambda is an eigenvalue of t, then mt of lambda is also 0. Lambda is an eigenvalue of t, therefore, there exists a non-zero vector v such that t v is equal to lambda v. Therefore, mt of t of v is mt of lambda v, but mt of t is the 0 operator. Therefore, mt of t of v is 0, and that is equal to mt lambda v. Therefore, mt lambda must be 0 because v is a non-zero vector. A remark: suppose that the characteristic polynomial chi t is given by this factorization, that is lambda 1 minus t raised to m1 and so on up to lambda k minus t raised to m k, where lambda 1 etc. up to lambda k are the distinct eigenvalues of t and m1 etc. up to m k are the algebraic multiplicities of the eigenvalues lambda 1 etc. up to lambda k respectively. Then, as a corollary to the above theorem, we can write that the minimal polynomial mt of t is given by the factorization lambda 1 minus t raised to e1 and so on up to lambda k minus t raised to e k, with the property that the integers ei are positive and they are less than or equal to mi for every I from 1 to k. Why is this true? Because of two things. One is that the minimal polynomial mt must divide the characteristic polynomial chi t, and we have proved that they have the same set of zeros. Therefore, the linear factors would be the same. The only difference will be in the powers of the linear factors in the factorization of these polynomials. Now, this theorem talks about the minimal polynomial of an operator restricted on a t-cyclic subspace. So, let T be a linear operator on a vector space V of dimension n over the field F. Let V be a non-zero vector in V. The minimal polynomial and the characteristic polynomial of the operator T restricted to the t-cyclic subspace TV have the same degree, and hence chi of T restricted to TV is equal to minus 1 to the power n m of t restricted to TV. Let us understand this theorem with the help of an example. Let V denote the vector space of all polynomials of degree at most 2 with real coefficients, and T the differential operator, that is T of f is equal to f dash. Let B denote the standard basis for V, that is 1 x square. We have seen before that the characteristic polynomial of the operator T is minus T cube, and we know that the minimal polynomial of T is a monic polynomial and it must divide the characteristic polynomial. Therefore, the options for the minimal polynomial are T, T square and T cube. We also know that the operator T satisfies the minimal polynomial. Therefore, if T square is the minimal polynomial, then capital T square, that is the minimal polynomial evaluated at the operator T, that must be the 0 operator. But we know that this particular operator, which is T of f is equal to f dash, that operator does not satisfy this T square equal to 0. Why? For example, if we apply T square on the polynomial x square, then the answer will be 2 and that is not 0. Therefore, T square does not vanish on the whole vector space V, and definitely this operator is a non-zero operator. So, the possibilities T and T square are ruled out, hence T cube is the minimal polynomial of the operator T. So, the only difference in the minimal polynomial of T and the characteristic polynomial of T is in the sign, as you can see in this theorem above. And what is to be noted here is that the vector space R2x is indeed a T cyclic subspace generated by the vector x square. Now, we state and prove another criteria for diagonalizability in terms of the minimal polynomial. Let T be a linear operator on a vector space V of dimension n over the field F. Then T is diagonalizable over F if and only if the minimal polynomial of T is of the form mt of T is equal to T minus lambda 1 multiplied by T minus lambda 2 and so on T minus lambda k, where lambda 1 etc. up to lambda k are the distinct eigenvalues of T. Proof: suppose that T is diagonalizable. Let us denote this polynomial T minus lambda 1, T minus lambda 2 etc. up to T minus lambda k as mt. Then mt divides mt of T, that is this polynomial mt divides the minimal polynomial. Let V1, V2, Vn be an eigenbasis for V, which exists because T is diagonalizable. Then given Vi, there exists an eigenvalue lambda j such that T minus lambda j I of Vi is 0. Now, since T minus lambda j divides the polynomial mt, it follows that m of T Vi is the 0 vector. Therefore, m of T is 0 on all the basis vectors V1, V2, Vn, and therefore, m of t is the 0 operator, but this proves that mt must be equal to mt of t, the minimal polynomial of t. Therefore, the minimal polynomial is of the desired form. Conversely, suppose that the minimal polynomial of t is given by this factorization into linear factors, that is t minus lambda 1 into t minus lambda 2 etcetera up to t minus lambda k, where lambda 1 etcetera up to lambda k are the distinct eigenvalues of t. Now, we proved that t is diagonalizable, and the proof is by induction on n, which is dimension of V. If n is 1, then t is obviously diagonalizable, there is nothing to prove. Suppose that n is greater than 1 and assume that t is diagonalizable if dimension of V is strictly less than n. Let us consider this subspace R, which is the range of the operator t minus lambda k I. Remember that lambda k is one of the eigenvalues. Then R cannot be the whole of V, since lambda k is an eigenvalue. If R happens to be the singleton 0 vector, then of course t is equal to lambda k I and hence diagonalizable. So, let us now assume that dimension of R is strictly bigger than 0 and strictly less than n. We know that the subspace R is T invariant, and if we choose any vector V in R, then T minus lambda 1 I multiplied by T minus lambda 2 I and so on T minus lambda k minus 1 I of V is the 0 vector. Therefore, the minimal polynomial mt restricted to R of the operator t restricted to R divides the polynomial t minus lambda 1 multiplied by t minus lambda 2 and so on up to t minus lambda k minus 1. So, by the induction hypothesis, t restricted to R is diagonalizable over the field F. Therefore, the intersection between R and the eigenspace n lambda k must be trivial, that is the singleton 0 vector. Let us choose an eigenbasis for R consisting of V1, V2, Vr. So, they are eigenvectors of the operator t restricted to R and hence of t, and let us choose a basis for the eigenspace n lambda k consisting of the vectors w1, w2 and so on up to ws. Then the intersection of these two bases V1, V2, Vr and W1 to Ws is MT, and the total number of vectors that we have is R plus S is equal to N, that is by the rank nullity theorem, and it is easy to verify that this set B, which is the union of V1, V2, Vr and W1, W2, Ws is linearly independent over F. Therefore, the set B has exactly n vectors and it is linearly independent, and V is also a vector space of dimension n. Hence, we have a basis for V consisting of eigenvectors of T, which proves that T is diagonalizable over F. We have therefore seen two criteria for diagonalizability, one in terms of algebraic and geometric multiplicities of eigenvalues and the other in terms of factorization of the minimal polynomial. We will see later on that the minimal polynomial plays a very crucial role when we talk about canonical forms for linear operators, especially when a linear operator is not diagonalizable, then we will see that under some conditions it can be put into some special form which becomes extremely useful, especially when we use them in differential equations and other contexts.